For most of human history, the universe was the Milky Way. Every object visible in the night sky, every glowing smear of light, every spiral cloud in the darkness, was assumed to belong to the same single structure that contained our own sun. Tonight, I am here with Rowan Hartsteele.
Good evening, Clara.
There is a man who looked at those smears of light and proved, through patient and precise observation, that they were not clouds within our galaxy, but entire separate galaxies, each containing hundreds of billions, stars, scattered across a universe far larger than anyone had dared to propose. Tonight, we turn to an astronomer who did not simply discover new objects in the sky, but permanently altered the frame through which all of humanity understands its place in existence. The question before us is how one man's work at a mountain observatory in California forced the entire scientific world to accept that the universe is incomparably larger and stranger than it had ever imagined.
The answer begins not with a telescope, but with a debate, one of the most consequential scientific arguments of the 20th century, about what the faint spiral objects in the sky actually were.
We are speaking about Edwin Hubble.
Edwin Hubble was the American astronomer whose observations at Mount Wilson Observatory in California demonstrated that the universe extends far beyond the Milky Way, and that the universe itself is in a state of expansion.
Then let us begin with the world that Hubble was born into, and the scientific context that made his discoveries possible.
Edwin Powell Hubble was born on the 20th of November, 1889, in Marshfield, Missouri, a small town in the American Midwest. His father was an insurance executive, and the family moved several times during Hubble's childhood, eventually settling in Wheaton, Illinois, where he attended high school. He was a gifted student with a broad range of interests, excelling in mathematics and science, but also in athletics. He was a strong competitive runner, and later a skilled amateur boxer.
Though he was not the archetype of the withdrawn scholar, he combined intellectual ability with physical confidence.
Yes, and that self-assurance would later define how he navigated the competitive and sometimes contentious world of professional astronomy. He enrolled at the University of Chicago in 1906, where he studied mathematics and astronomy under some of the leading figures of the field, including the astronomer George Ellery Hale. But at his father's insistence, he also agreed to study law. After his father's passing, he fulfilled that promise by reading law at Oxford on a Rhodes Scholarship before returning to the United States in 1913. He practiced law briefly in Kentucky, found it deeply unsatisfying, and made the decision that would define his life. He returned to the University of Chicago to pursue a doctorate in astronomy and...
So the path to the observatory ran through a legal career that never took hold.
Yes, and the detour matters because it delayed his entry into professional science until his mid-20s, which made the speed of what he would subsequently achieve even more remarkable. He completed his doctorate in 1917, writing a thesis on the photographic investigation of faint nebulae, the very class of objects that would occupy the central years of his career. Shortly after completing his degree, he served in the First World War, reaching the rank of major, before joining the staff of Mount Wilson Observatory in California in 1919.
So Mount Wilson was where everything began.
Yes, and to understand why Mount Wilson was so significant, we need to understand what the Hooker telescope made possible. The Hooker telescope, completed in 1917, had a mirror 100 inches in diameter, making it the largest optical telescope in the world at the time. Its light-gathering power was so far beyond any previous instrument that it could resolve individual stars in objects that had previously appeared only as diffuse glowing patches. This meant that for the first time, astronomers could look inside the spiral nebulae and see what they were actually made of, rather than simply measuring their shape and brightness from a distance.
So the instrument arrived at exactly the moment when astronomy needed it.
Exact. And here we must pause to explain the scientific debate that Hubble entered when he arrived at the observatory. For decades, astronomers had been cataloguing and debating the nature of what were called spiral nebulae, faint luminous structures with a characteristic spiral shape visible through telescopes in many parts of the sky. The dominant view, held by many of the most prominent astronomers of the period, was that these nebulae were relatively nearby structures within or just beyond the Milky Way, perhaps early solar systems in formation. A minority view, sometimes called the island universe hypothesis, held that they might be entire separate stellar systems, comparable in scale to the Milky Way, located at enormous distances.
So the debate was really a debate about the size of the universe itself.
Exactly. If the nebulae were within the Milky Way, the universe was essentially the Milky Way. If they were separate galaxies, the universe was orders of magnitude larger than anyone had measured. This debate had been formalized in a famous public exchange in 1920 called the Great Debate, in which the astronomer Harlow Shapley argued forcefully for the smaller universe, and Haber Curtis argued for the smaller island universe hypothesis. The debate ended without resolution because neither side had observational evidence precise enough to settle the matter. That evidence was what Hubble was about to produce.
So Hubble arrived at the observatory just as the central question of astronomy was waiting to be answered.
Yes, and the key to his answer was a particular type of star, called a Cepheid variable. Cepheid variables are stars that pulsate rhythmically, brightening and dimming with a regular period. The astronomer, Henrietta Swan Leavitt, had established, through painstaking analysis of photographic plates, that the period of a Cepheid's pulsation is directly related to its intrinsic luminosity. This meant that if you observed a Cepheid variable, and measured how long it took to complete one cycle of brightening and dimming, you could calculate how intrinsically bright the star actually was. And if you knew how bright a star truly was and could measure how faint it appeared from Earth, the difference between the two values told you how far away it was.
So a Cepheid was a ruler built into the stars themselves.
Exactly. Astronomers call it a standard candle, a light source whose true brightness is known, so that its distance can be calculated from how dim it appears. In the autumn of 1923, Hubble was photographing the Andromeda Nebula with the Hooker telescope, when he identified a star within it that showed the characteristic behavior of a Cepheid variable. He measured its period and used Leavitt's relationship to calculate its intrinsic brightness. Then he compared that brightness to how faint the star appeared from Earth. The result was staggering. The star was approximately 900,000 light-years away. The Andromeda Nebula was not inside the Milky Way, it was far beyond it.
So, a single measurement collapsed an entire framework of assumptions about the size of the universe.
Yes, and this is the moment where the popular myth must be corrected. The discovery was not a sudden flash of inspiration. It was the product of years of careful photographic work, night after night on the mountain, building a systematic catalogue of measurements. Hubble did not simply look through the telescope and see galaxies. He accumulated photographic plates, measured the positions and brightnesses of thousands of stars, and applied a precise mathematical method, developed by someone else entirely. The discovery was a triumph of systematic observation, applied with rigorous consistency, over a long period of time.
So the heroic image of the lone genius at the eyepiece misses the actual texture of the work.
Completely. Henrietta Swan Leavitt, whose period-luminosity relationship made the Cepheid distance method possible, worked at the Harvard College Observatory as what was called a human computer, a woman employed to analyze photographic plates for very low wages. Her fundamental contribution to the tool that allowed Hubble to make his discovery was not fully acknowledged in the recognition he received, and she had passed away in 1921, before the discovery she made possible was announced.
So the discovery stands on a foundation built by someone who never received credit for it in her lifetime.
Yes, and holding that fact alongside the celebration of Hubble is important if we want to understand how science actually works as a collective and sometimes unequal enterprise, rather than a sequence of solitary triumphs. Hubble published his findings in January 1925 in a paper presented to the American Astronomical Society. The response was immediate. The debate that had divided astronomy for decades was resolved. The spiral nebulae were galaxies. The universe contained structures comparable in scale to the Milky Way, at distances so vast that the light reaching Earth from them had been traveling for hundreds of thousands or millions of years.
Though the announcement did not slowly percolate through the scientific community, it landed and the field reorganized around it.
Yes, and Hubble did not stop there. In the years following his initial discovery, he extended his catalogue systematically, identifying Cepheid variables in further galaxies and building a map of the universe at a scale no one had previously attempted. But the second and in some ways more consequential discovery was still ahead of him. Earlier in the 1910s and 20s, the astronomer Vesto Slipher had measured the spectra of light from spiral nebulae and found something strange. Most of them showed a systematic shift of their spectral lines toward the red end of the spectrum. This red shift indicated, through a principle analogous to the Doppler effect in sound, that these objects were moving away from the observer at high velocities.
So even before Hubble confirmed they were galaxies, there were measurements suggesting they were moving.
Yes, but Hubble combined Slipher's velocity measurements with his own distance measurements, and found a striking pattern. The farther a galaxy was from us, the faster it appeared to be moving away. The relationship was not random, it was linear and consistent. Double the distance, roughly double the recession velocity. This proportional relationship became known as Hubble's law.
So the universe was not simply large, it was getting larger.
Yes, and this is the turning point in the story, because the implications of that observation reached far beyond astronomy. And if the universe is currently expanding, and all galaxies are moving away from one another at velocities proportional to their distance, then running that process backward in time implies that the universe was once much, much smaller, much denser and much hotter. It implies an origin point, a moment in the deep past from which all of space and time began to expand. That idea would eventually become the foundation of what we now call the Big Bang model.
So Hubble's observations of moving galaxies contain, hidden within them, the origin of the universe.
Yes, and it is worth noting that Albert Einstein had already derived equations from his theory of general relativity that predicted a non-static universe, one that was either expanding or contracting. Einstein had been so troubled by this implication that he introduced an artificial term into his equations, what he called the cosmological constant, specifically to force his mathematics to produce a static universe. When Hubble's observations confirmed that the universe was in fact expanding, Einstein visited Mount Wilson in 1931 and reportedly acknowledged that the cosmological constant had been his greatest mistake.
So Hubble's data corrected Einstein's intuition about his own equations.
Yes, in that moment, the world's most celebrated physicist, visiting the Mountain Observatory to confront what the data had said, is one of the defining scenes of 20th century science. It represents the point at which theoretical physics and observational astronomy converged on the same conclusion through entirely different methods, which gave that conclusion extraordinary authority.
So, the theory and the telescope arrived at the same place.
Exactly, and that convergence is important for understanding why Hubble's discoveries were accepted so rapidly and so completely. Hubble himself was careful and somewhat conservative in how he interpreted his own results. He consistently preferred to describe the redshift as an apparent recession velocity rather than a definitive confirmation of expansion, leaving the theoretical interpretation to others. This caution was partly temperamental and partly strategic. He understood that extraordinary claims required extraordinary evidence, and he preferred to let the observations speak with minimal theoretical embellishment.
So the man who reshaped cosmology was reluctant to commit to the cosmological conclusions of his own data.
Yes, and that restraint is itself a lesson in scientific discipline. He continued working at Mount Wilson, and later at the Palomar Observatory, where an even larger telescope was eventually constructed. Throughout the 1930s and 40s, he developed a classification system for galaxies by their visual morphology, distinguishing between elliptical, spiral, and irregular forms, a framework still used in modified form by astronomers today.
So he also built the basic vocabulary for describing what he had discovered.
Yes, and that is often the work that follows a great discovery and that proves equally durable, not simply finding new things, but creating the conceptual tools with which others can study and categorize them. Hubble served again in the military during the Second World War, working in ballistics research at the Aberdeen Proving Ground in Maryland, and returned to astronomy afterward. He suffered a heart attack in 1949, and another in 1953, the year his life ended. He had been scheduled to use the New Hale telescope at Palomar for the first time when he passed away in September of that year.
So his life ended at the threshold of the next instrument that would have extended his work.
Yes, there is a particular poignancy in that timing. The man who had spent his career at the frontier of what instruments could see ended his life standing at the door a larger one.
Before we close tonight, let us take a brief pause and welcome Margaret Evernight. Margaret.
Thank you, Claire. In this case, the most direct path is also the most important one. I would suggest beginning with Edwin Hubble, Mariner of the Nebulae, by Gail E. Christensen.
So this is a work that follows Hubble from his education through to the discoveries that remade our sense of the cosmos.
Precisely. Christensen traces the full arc of Hubble's life and career, from his early education to his groundbreaking work at Mount Wilson, where he demonstrated that the spiral nebulae were distant galaxies entirely beyond the Milky Way. The book also places Hubble within the broader scientific and technological developments of his era, showing how advances in telescope construction and astronomical measurement made his conclusions possible.
Is it accessible to a reader who is not already familiar with the science of cosmology?
It is genuinely approachable. Christensen explains the scientific context with clarity and keeps the human story of Hubble's ambition and discipline at the center, so the technical material never overwhelms the narrative. It is the kind of biography that leaves a reader understanding not only what Hubble discovered, but why it was so difficult and what it took to arrive at those conclusions.
So reading it gives a reader both the science and the human effort behind it.
Yes, and it leaves you with a genuine sense of how large the universe became in the space of a single career.
Thank you, Margaret. That is a thoughtful place to pause tonight.
Thank you, Clara. It was a pleasure.
The immediate legacy of Hubble's discoveries was a fundamental reorganization of how astronomy understood its own subject. Before his work, astronomy was largely a science of our own cosmic neighborhood. After it, the universe became the subject in its full, unimaginable extent. The discipline of extragalactic astronomy, the study of objects beyond the Milky Way, came into existence as a direct consequence of what Hubble demonstrated. It is now one of the most active fields in all of science.
So his discovery did not just answer a question, it opened an entirely new domain of inquiry.
Exactly, and the influence on theoretical physics was equally transformative. Hubble's law, the observed relationship between distance and recession velocity, provided the empirical foundation upon which the Big Bang model was eventually built. The Belgian priest and physicist Georges Lemaitre had proposed a primeval atom hypothesis as early as 1927, but it was the observational weight of Hubble's data that gave expansion-based cosmology its scale, authority. The Big Bang model, which describes the universe as having originated from an extremely dense and hot state approximately 13.8 billion years ago, rests on expansion as one of its central pillars.
So the pattern Hubble observed in his photographic plates contains within it the origin of everything.
Yes, and that is not a metaphor. It is a precise statement about the logical structure of modern cosmology. The critiques of his legacy are also worth examining. Hubble was at times resistant to crediting others, including Milton Humason, his observational collaborator at Mount Wilson, who contributed substantially to the velocity measurements underlying Hubble's law. He was also at times aggressive in pursuit of professional recognition, and was not always generous toward contemporaries who had contributed to the same questions.
So the man who expanded humanity's view of the cosmos did not always take an equally expansive view of his colleagues.
Yes, and the question of whether he deserved the Nobel Prize, which he actively sought and never received because the Nobel Committee did not at the time consider astronomy a branch of physics, remains a source of discussion. He was under consideration when his life ended in 1953. The Nobel Prize is not awarded after a candidate has passed away, so the question was never resolved.
So the man who found the boundaries of the universe was stopped at a bureaucratic boundary himself.
Yes, that irony has not been lost on historians of science. The most visible modern tribute to his work is the Hubble Space Telescope, launched in 1990 and still operational, which bears his name and has produced some of the deepest images of the universe ever recorded. The Hubble Ultra Deep Field Image, which captured nearly 10,000 galaxies in a region of sky no larger than a grain of sand held at arm's length, is perhaps the most direct visual demonstration of what his life's work implied. In every direction we look, at any scale we can measure, the universe is filled with galaxies in their hundreds of billions, all receding from one another in an expansion that began before time as we understand it had any meaning.
Though the image the telescope bearing his name produced is the fullest possible expression of what he discovered.
Yes, and the enduring relevance of Hubble's discoveries for how we understand ourselves is perhaps the deepest part of his legacy. Before him, humanity occupied a universe that was, in a meaningful sense, our universe. The Milky Way was the cosmos, and we were near its center. After him, we inhabit an unremarkable planet orbiting an unremarkable star in an unremarkable corner of one galaxy among hundreds of billions, all embedded in an expanding universe whose scale and age dwarf anything human thought had previously imagined.
Though his discovery did not make us smaller, it made the context we inhabit incomparably larger.
Yes, and today, as cosmologists use instruments of extraordinary precision to measure the expansion rate of the universe and debate its ultimate fate, every one of those conversations begins with the observations that Hubble made from a mountain in California in the early decades of the 20th century. The question of what the universe is doing and where it is going is still open, but it could not have been asked without him.
Thank you for staying with us tonight. And thank you, Rowan.
He looked at faint smears of light and returned to tell us that each one was a universe unto itself.
If this conversation stayed with you, you are welcome to like, comment, and subscribe. You will find other episodes here where history, ideas, and power are approached slowly. Until next time, stay with us.